All right, yeah, welcome everyone inside the room and also welcome to the online audience as well. Today we start the high performance computing course, a course that goes back for 8, maybe now 10 years here at the university. So basically that means we have lots of experience already put into the course from student feedback, from topics that are relevant. But also this year we will have a little bit a kind of CFD special, a computational fluid dynamics special, in the second part of the course that is taken over by my PhD student Reza. I have lots of research projects, so I need to teach much less. Basically, then he can help us and take over the teaching. Still, the topics of the course will be very relevant for high performance computing. And the many logos you see here will be explained throughout basically my presentations that in one way or another usually gives us some funding. That's why we basically have it also on YouTube available for the whole community when you talk about, online teaching and so on. I think someone online, could you please mute? Thank you. The idea and the outline of the course is basically as follows. We have a very, let's say, basic introductory setup from high performance computing in the first couple of lectures. You see, it's a little bit a mix of practical and theoretical topics. Usually the practical topics are around some assignment that you have to perform in the course. We talk more about this later. And then we go to more deep learning topics where HPC now makes a big difference with GPUs. We'll talk about that. And then we'll enter more or less, as I said earlier, the second part, which is a special edition this year, where Reza then takes over a little bit and talking with you really as a fluid expert, actually publishing a lot in this field about this course. Every now and then you will see in between, there will be practical lectures where we demo something. There will be practical lectures coming from industry experts that will basically do maybe a presentation about Rescale and others also that are here in Iceland. So with this, we basically have today rather the not real first course hours. It's just for you a little bit the prologue to get warm up, to maybe clarify some questions, to see where actually HPC fits in the bigger realm. And what we do in this HPC course is essentially cover the basics of high performance computing, which is quite fantastic. I'm 20 years in the field. I can say I love it. And I would encourage you to look at this field. It's always at the cutting edge of computing, Formula One of computing, the biggest systems, the boldest systems. But basically, this is also driven by so-called domain sciences. And this computational fluid dynamics that we have in this course this time is really one of these special domains which leverage HPC a lot. Right, hence we always have in this course a little bit of, let's say, normal basics of how you do parallel computing. This could be with these two paradigms, MPI with message exchanges from one processor to another, or you do something like shared memory programming. Doesn't mean anything to you. We will see how that materializes then basically throughout this course. But these are the paradigms how we do parallel computing on high performance computing. More recently, GPUs have been in the game as well. And this is something what we tackle basically from the topics. You see on the right hand, these applications that basically leverage HPC a lot, car crashes, smoke. Let me see, that should be a video, basically, how you basically want to compute how a kind of tunnel and how basically there the smoke will be from a fire or so, basically progressing through a tube as an example. Earth sciences with different climate models on different areas inside the Earth's realm, or wind in Iceland. These are all in one way and example applications that we here and there cover throughout the course, but we basically focus a lot this time basically on the second part in these applications. However, if you're interested in earth science and others, my courses from the last years are all on YouTube, right? So these lectures are all there. And in the final project, which we will explain a little bit, you will also have the possibility maybe to go into another topic if you like. So much for the general understanding where the course fits. High performance computing draws lots of benefits from parallel processing, distributed computing. Also this we will have a look in what this actually means in terms of HPC, why we do then high performance in this respect. This area is very much driven with scientific computing, hence we're not going for MATLAB or Maple or the simple scikit-learn things, which are a little bit like serial. We really think about the big scale, how you want to do, let's maybe the turbine of an aircraft. So really the cutting edge applications that you need. And for this, basically you see the demand always fueling HPC because it's very costly machines. And of course, they are then having the right to exist because we have so many scientific requirements and engineering requirements in order to make this happen. Then this basically means at the end of the course, you have some knowledge of how to do advanced scientific computing. Some people say scientific computing is rather this, what you do is METL or MATLAB and all this, let's say, more serial tools. But then the advanced scientific computing, how you can really use large parallel computers with parallel computing in order to basically have either simulations of the reality, which is one part of the game. We call that the simulation sciences based on, numerical methods based on known physical laws, for instance. This is more the idea of physics behind it. And more recently, we have also learned that the field of machine learning, deep learning, has also some role to play in this area of science and engineering. And is, of course, also fueled by HPC with a lot of GPUs that we use in parallel. Some of my research scientists use up to 500 or 1,000 GPUs in parallel, right, in order to fix a scientific problem, which is not a toy problem like a character recognition problem, but real kind of, for instance, satellite image analysis or so with multispectral data up to 200 dimensions. So in the end, that's the idea what you should have in mind when you come to this course. Really think a bit bigger than your little laptop. And basically with the CFD, you already enter in a very nice area of HPC. So again, there we have some flexibility at the end. Riedel will teach there a lot. But for the final project, we can have also some other applications where you maybe have some mechanical engineering problem, just as an example, or as we had from you all have a bit a different background, maybe we can also adjust there the final project. From the understanding, it's really a lot of topic and names that you maybe don't really at first know. We will have lecture by lecture, of course, starting with this now slowly tomorrow, where we warm up a little bit with Unix, we warm up a little bit with SSH, C programming. The amount of C programming is very little here in the course. Usually the codes are already existing and you execute it, so don't worry about this. But in HPC, Fortran and C is basically still the big languages to speak in simulation sciences and physics. If you go maybe to the domain of machine learning, deep learning, then you have a bit Python, right? And you put the notebooks and so on. But basically, the amount of programming here needed is not that hard. It's more rather understanding the parallelism. And this will be a bit complex because you don't think about only one core or two cores anymore, but a couple of cores solving one problem jointly together. And this is what we call parallel programming, parallel processing. And over this, we have some different levels of abstractions. You will see the cloud computing course that some of you have been part of. Was a little bit higher level, right? The cloud is nice and shiny, and you have a service that does everything. Here in basically in the HPC course, we go a little bit deeper and understand really what is memory behind it, how we do the message passing between one of the different, applications in the different processes that we have available. So, and sorry for being always in the back of some of you here, but so this is something which means we have a little bit of different abstraction, meaning we stay within basically one node and can do a little bit of shared memory programming, but it's very, very limited, still very fast because memory is very fast, but very limited in the sense that we are in one core and in one node. And if you want to do across nodes, you basically do the distributed memory programming. And of course, then the idea is to even basically combine both. I know we have some question marks now. That is something which we will learn now step by step in the next couple of weeks together. So in the end, I think you should really understood HPC when you finish this course. Also the understanding what you need to do a simulation. Let's say just simulate this room, open the window with the fluid flow coming in, air ventilation, all of this, how you basically could tackle this with parallelism, where you also have the knowledge of domain decomposition that you simulate, of course, these in different fractions of the different, processors, a little bit illustrated here with all these different boxes of the machine that, of course, the parts of the applications are very distributed across the computing. And yeah, with this, the parallelism complexity is something, of course, which will come back. You will see you cannot do a simple debug or something that doesn't work because you're very distributed across many many different processors. So much more complex, and this is what we want to teach. This is a little bit the machines and the background from us, maybe also a little bit so that you know why we have the right here to stand. I'm 20 years in this Jülich Supercomputing Center, which is a leading European supercomputing center. We will get an exascale system in 2023, 2024. And it's one of the centers of the Helmholtz Federation. Is someone from Germany here? No? You saw it a bit. So you know maybe a bit Helmholtz. It's a big German association for research centers. And the one basically where I got lots of expertise over the years is basically this Jülich Supercomputing Center. We already collaborate with Iceland since 2012. So we have lots of PhDs back and forth doing, let's say, their degrees here. And of course, also having workshops where the people from this center come here. You will be participating in this. I hope that we will have mid of February. As you in the cloud course know that already, our eHPC workshops will continue. Basically, the one in February and April, I will invite you and bribe you a little bit with some credits for your final projects that you participate. But there you have also the chance to really get some experts in the field that are basically very long already working in the domain of HPC. So the way why we do this is basically, this is a national lab that you just seen. So basically there we cannot be professors. And what we do is usually we team up with different universities in the world to get our professorships, still maintaining our position at the research group. And this is a fruitful exchange, fresh students for the research center. And of course, the research center has, let's say, an exascale system which no university can afford, right? So it's a back and forth basically that you see here. And just a couple of things about me, again, why I should stand here in front of you doing this course. One highlight was basically also that I was designing the US HPC infrastructure. I think I've seen some of you are basically also from Berkeley and from other US institutions. There's a program called Exceed. It's actually now finished, but basically was also kind of a really large endeavor. In our European fraction, we had like 25 million. In US, we had available 125 million. So you see there's also a little bit more scale, much bigger systems available. But it was a very interesting project. And you see all the other projects working with CERN. Some of you maybe know CERN, the Large Hadron Collider or so, right? So there I was quite involved as one of the directors there for software and middleware, as we call the access to HPC systems. So also they're managing teams from up to 70, software projects, leveraging HPC and data intensive parts. We should not forget HPC, because it's so much computing, was also big data long before basically the industry picked up the big data term. Nowadays, I'm also the kind of Europe HPC. I will explain a little bit what that means later. Governing board member of Iceland, basically the highest board in HPC in Europe for decisions, what we do as community. This is also, of course, in the moment, quite a nice position to be, to shape really the future of HPC in the next years, at least in Europe, right? So that's what we can say. And needless to say, a lot of teaching in the research center Jülich for 20 years, but also here at the University of Iceland, we had over the past many different courses that all in one way or another took basically part in parallel programming and leveraging HPC systems. Now I need to talk about Reza, but I think I just gave you the microphone.
Thank you, Maurice. Hello, everyone. I'm Reza. Currently, I'm a PhD student working with Maurice. I am a member of the research group supervised by Maurice. My focus on my PhD, applying the high-performance computing and artificial intelligence in the fluid dynamic area and CFD. As well, I am a member of the National Competence Center of Iceland, and we have a community in the simulation and data lab computational flight dynamics. Recently, in my study, we applied the high-performance computing and artificial intelligence in the fluid dynamic and turbulence flow, and we had some novel achievements. And in this lecture, in some practical lecture, we will talk about them. So I'm so glad to be in this course. and I hope you will enjoy this course and you have some idea from this course, maybe for a future project, for your master thesis. And please feel free to contact me during the course if I can help you. Thank you, Maurice. I'm leaving to you.
All right. Thank you very much, Reza. I can also confirm he is really an expert in the fluid domain, quite a, I would say, senior PhD student already with lots of publications. I'm very glad to work with him, and he will be a very good teacher, I'm very sure. And he has also taught courses before, so you will be in good hands. Continuing a little bit what we do more generally here at the School of Engineering, and basically we are called the School of Natural Sciences and Engineering, the SENS, that you probably has already noticed. We're quite strong in remote sensing. This is something what we also drive ahead in HPC quite a lot in the simulation and data lab, remote sensing. And we have lots of international students as well. So you will see that this course has quite some US students or Erasmus students or many foreign students. That's why we also teach a lot in English. And it's very practically oriented sometimes. So we have very close contacts to industry, to commercial partners to really also do what we do here in kind of theory in the lectures, also in practice with companies and so on. Needless to say, we have also good contacts to basically HPC companies, or let's say companies which are related to HPC, like data centers, for instance. When you want to have your jobs, we can also help you there a little bit. Then when you think about the detail, how we work together with the German center, also in terms of this research group that we mentioned, is basically a joint venture of the Jülich Supercomputing Center in Germany and also the University of Iceland. We basically have this research group around 10 years now with lots of PhDs going back and forth. In the meantime, we have also 2 professorships nowadays. One of my PhD students that graduated here in Iceland was also hired by Jülich, and over time also made it now to a professor here at the University of Iceland, Gabriel Cavallaro. So our bonds are very strong with this supercomputing center. And of course, needless to say, in the HPC course, we will touch base on some of these logo projects here that you basically see, the Center of AI here, for instance, Center of Excellence of AI. Some topics will be raised by Reza later, but we will also have some general aspects of different projects that you have already heard, the deep projects, for instance, the modular supercomputing approach, and so forth. But what you more clearly also see in this picture is that really the facilities, the supercomputers that we have, are typically driven by the demands of sciences, so-called simulation and data labs, some cross-sectional teams, but really scientific engineering problems that really need these facilities. And communities drive these usually in different areas of health, in remote sensing, medicine, and all the different areas of physics, like computational fluid dynamics, for instance, that Reza will also talk more about in this course. Hence, the supercomputers are not just there and, you know, are big, bold to wait for anyone to come. It's usually also a co-design process that we do from all of these different applications that we see. And these domain-specific simulation data labs we have also at the National Competence Center here in Iceland. And that's something what we will also explore during the course, basically here in our lecture series. Also, as basically you already said, we have a community page. I would encourage you to look at our National Competence Center funded by the EuroCC 2 and 1 projects in the past with different simulation and data labs that actually capture now the story of this domain-specific sciences using HPC. So you see not only fluid dynamics, but also remote sensing, language processing, different areas of engineering and science, which actually use the HPC. And if you are in one area or interested in one area, I encourage you to look that up. And basically all of these sim labs in one way or another are also involved in all of these research projects and fund also some of these activities. Hence, there's master thesis projects available in these different areas of sciences if you want. And of course, even there are PhD student positions also available. Just for understanding the general paradigm, we will talk about this, of course, from tomorrow on more and more and more. just to get the overall idea from HPC, it has always something to do that you bind lots of computing pieces together. So cores, of course, in one respect on the chip, but we're thinking much more broadly in terms of nodes, different nodes all in these racks. And the important difference, for instance, to the term HTC, high throughput computing, is that HPC really leverages the interconnect, right? It's very costly, the interconnect, something like InfiniBand, to really bring these boxes together. Otherwise, you could have just a couple of distributed loose boxes somewhere with an Ethernet cable or so connected. This is not basically HPC. HPC is much rather leveraging the interconnect. And if you see many of the cloud computing paradigms and these related concepts work on this area, while HPC applications, let's say, really weather forecast is significantly drawing on HPC, because every tile, when you have a big domain like the Earth chopped down in parallel pieces, will infect the others somehow. Hence, there needs to be good connectivity. And we will talk about this in the course, of course, up and down. Another way how to understand HPC is perhaps what you see here in one of the systems we had in Jülich, when they built a second floor, for instance, underneath, where they did an upgrade from one system to another. So these are all different racks, all plunged with different cores and different chassis. We will talk about this in the course as well, just for you to understand that it relates to this floating operation per second, which is the metric, so to speak, how we basically measure a high-performance computing system. And you could say in the 80s, this laptop was a high-performance computer, right? It did lots of flops. And now over the time, you see from 2009, we had then suddenly already quite more flops available, and it's constantly rising because the number of cores are also constantly increasing. Hence, this is a system machinery, so to speak. You cannot just put somewhere in a university cellar and then run it. You need a really big, large facility where you have also maybe fire protection with gas rather than water, for instance. Here, some of you are familiar that our cellar was here kind of flooded once. So this is probably not so good for a HPC computer. Here's a bit a kind of history, how we basically evolved over the last 20 years. Since I'm starting in HPC around 2003 and 2004, where there was one system. Nowadays, we have, so to speak, more modular supercomputer, where we have some general purpose cluster with high single thread performance CPUs, and some highly scalable ones where much more GPUs are in and kind of many core units. All of these names and terminologies we will talk about, right? And we will define throughout this course. And we'll also provide you some details, just that you get a general feeling in which area we dive into in the course. Here and there, we will also talk about some important projects. This is one important one because it created the modular supercomputing architecture together with our industry partners from Fraunhofer, or I think Partech was involved, Extol, and so on. And this influenced a lot how we use supercomputers in Europe today. Which you see a little bit here again from all the different areas of sciences. Many of the system designs are built now on this modular framework, and we will also use in one of our assignment, basically one of these deep systems, a modular supercomputer, again with a cluster node with high single thread performance, a booster node with many core GPUs, data analytics for Spark and other memory intensive things, basically something we learned in the cloud course, right? So Spark and these are elements that leverage a lot of memory, but don't need really the interconnect so much. And of course, storage plays a big role as well. And the kind of idea how you use that in the future more and more is that you really do different areas, different modules connected. You see a quantum annealer, for instance, we use these days as well. For instance, to speeding up the optimization within a machine learning algorithm that would otherwise do iterative, basically analysis. And with a quantum annealer, we just do this and have the basically optimization result available. But we come to this in the course. And yeah, this is just one of the modules we will basically use, the data analytics module part in the course, and we will talk about this then later. There you basically should enroll to the project called JOIML, but this will be also something I will explain to you when we have the first practical course, which starts tomorrow. Just for the organization perspective, before we stop the first part and then we dive a little bit into what topics are there, it's a typical course. So we have a Canvas environment here at the university. Many of you know that from the other course. So it's basically the same modus operandi as all other courses have. It's now published. There are different modules. You can see that here a little bit. I think I opened it already. Right, and I will usually always have a recording that I will upload the day after, or let's say as soon as possible, for each of the different lectures. They will be announced. There will be always an online participation with Zoom available, and that's something also we want to discuss with you later, that we maybe turn the Monday lecture into a more virtual lecture because it's not so friendly for everyone. However, still, if you are having difficulties and so on, my suggestion is also to book an online, office hour, or maybe even in my office in Groska. But you really have to, let's say, contact us, just not pop in. My schedule is every hour taken, basically every single day, right? So that means we need to book a slot, same for Reza, in order to have an office hour. But that's of course possible with my assistant Katrin here, or also contacting then basically Reza. From the overall structure of the course, we will have 3 assignments, which are actually 40% of the grade, roughly. We have this at 10, 20, 10. Again, in terms of thinking about the final project, will overlap with the 3rd assignment. That's why basically the work of the 3rd assignment is also going lower again, so that you have more time for the final project. This will be 50% of the grade. And it's also a little bit new because we have polls to students all the years. And nowadays the students, not necessarily you in the room, but the majority say they don't prefer an exam anymore. They want to have a final project. So we change this also here and try to incorporate this into the, feedback of the course. And me and Reza, by having 2 teachers, we basically can make that happen. Speaking of which, you should have a good team. The assignments are always 2 to 3. Yeah, you're a good team, I know. So, but it's really crucial that you maybe find a good team. This time it's more crucial than before because you have also final project together, right? The final project will be again in the same team, if possible. If a team breaks, it's not a big problem, but usually we see performing teams in really, staying together through all the difficulties. You will see we don't have only maybe this course, you have also 2 or 3 other courses with some workload, and then a good team can really make a good balance, load balancing, as we would call it. But of course, it's completely up to you. Just inform us, please, what are the team members. This is not something you need right now. So the next couple of lectures, you can elaborate. There's also an discussion topic where we will start basically of saying, please get yourself team up together. But this year, I really recommend that you maybe have a session together online, or you meet in person to really get your chemistry with the other team members, so that you have a good team, which helps you probably also for the final project then to really perform well. As I said, there will be some invited lectures from some experts in industry we collaborate with, just to show you also that what we teach here has really kind of substance in the real practical fields and not just as a theoretical exercise. Every now and then we have this 10% of a grade quizzes in Canvas. This was previously always to prepare you for the exam from a more theoretical knowledge point of view, where the yellow blocks were quite important. So the quizzes, you can really perform well if you think about the yellow blocks. This time it is a bit less emphasis because the exam will be not a written exam anymore like the quizzes. So hence, it's just more to check your understanding of the course, but has a minimum input in the grade. As you see, 4 quizzes and 10% overall. So you would say 3% per quiz. So hence the structure of the course will be alongside this and the grading as well. I modified this a little bit here so that you see there's now a quiz 4, which is not anymore a test exam, but basically also normal quiz. And what's definitively changed here is then that the exam is not anymore, present, but we have this final project that we will hand out very early, of course, so that you have time to do that. And the rest you already know, or we can tackle in question and answers. I already announced that everything we do is on YouTube, also to make basically the people happy that fund our research a lot and our teaching, as you see with all the logos. Basically, you have the YouTube channel where each of the lecture will be uploaded. You have it from the 2022 course, 21 course, and I think the 2020 course is also already online. And we do the same with our lecture, we'll be always recording and uploading. The uploading can be sometimes taking a bit time because YouTube needs to kind of transfer, kind of render it and so on in different qualities. So it might pop up one day later or so, depending also on the cloud and Zoom when they come back to us with the recordings. But yeah, so basically this is always recorded. And if you want to know some other topics that we don't teach this year, you can always move back in these different YouTube channels and can, you know, have more information. More from the practical community side, as I said, I'm still an active researcher, so here and there maybe it's also quite nice to check social media. This has been taken up in the last 5 years a lot. Also talking with students that are liking much more social media than looking on old websites which are outdated. So there you can have a lively thread of what's happening in HPC, usually going a lot into conferences. I mean, here was a quite nice event you see where I was invited to the German Bundestag, which was my highest call here in my career, perhaps, to inform basically the whole federal parliament about what HPC AI and so to speak artificial intelligence in that context matter. So, but there will be lots of conferences, events where you see also how HPC can be more practically understood as part of the community, how we work together with scientific domain experts. And over the years, we incorporate lots of feedback into the course. As I said also earlier, each of the courses has lots of bibliography. You will see 3 pages, 2 to 3 pages in context every time if you want to learn more. Obviously, we can teach just this from the big field of HPC, but basically I provide you lots of pointers. And of course, I have lots of contacts all over the world in HPC. If you want to get in contact with some of the centers in somewhere in different member states of the EU or US, just let me know. But you also will find lots of this bibliography information for learning more. And you see also YouTube links to videos. I always do 2 videos basically per lecture, where I think it's also good to see the impact from HPC from other sides. It's also an important part there. And over time, I think we come to a course which was quite interesting. You see here from the lectures, there is some feedback we got from the course even online, basically through the YouTube audience that says very helpful for beginners, etc., etc. So this is, yeah, lots of things which are fluent coming also basically back from you. That's what I'm saying. So it was really an input from students over the years. And since we have this now on YouTube, we cannot really record anymore the videos. So YouTube is always doing striking and want to remove the videos. So we stop here the recording, but show the video afterwards. But you have the link to the video basically always in context so that you can look at also again online. But here it's just that we don't republish things from YouTube in our own recording, which is basically not a good thing to do in YouTube. So I stop the recording here and then we get going with the video.